Okay, good morning. Let's see.
Good morning.
Trying to see the thing that says we're recording. Well, let's see. Come on, help me out here. There we go. Security, video, more. Well, apparently we're recording. I just don't see the widget for it. Okay, so what's going on here? We are here, beginning the functional programming. This module takes 2 weeks. You will not become an expert in functional programming. You will not become an expert in the language that we're using, which is Racket. But you'll become familiar with the concepts, the ideas, and the way you have to think a little bit differently about how you approach an algorithmic solution to a problem in the functional world. It does follow directly from the lambda calculus module because it is a mapping from lambda calculus. So when the first few major languages were produced, one of them was Lisp, L-I-S-P, which is an acronym for list processing. That was a functional programming language. Anyone know the year? Don't Google it. 1958. So they've been with us for a while. Why have they not been as successful as the imperative style? Well, they were slower, is one of the larger reasons. And back in the days when chips were slow and memory was really expensive, people really worked hard to save every bit of their program to reduce the memory footprint and to save every computer cycle that you could. Now, chips are fast, memory is cheap, nobody cares. They are making some of a comeback. There are some problems that are just inherently functional, inherently recursive, and therefore amenable to the functional paradigm. And there are people, when you get into languages, you get into what we call religious wars, right? You get into people who argue that their language is the best no matter what, because. And, people who are functional programming paradigm advocates will tell you all about how wonderful functional programming is. There are some really cool features in there. One of the things is, as a rule, as a general rule, functional programming programs are about 1/3 the length of their imperative equivalents. And if you think in terms of all you software engineers in the class, if you think in terms of software maintenance, and software understanding and software cost of development, cost and time of development, number of errors that you need to debug, those things are all related directly to program size. So there are people who will talk about how clean this paradigm is. A few years ago, well, here's what's going to happen, right? I'm going to have you do some simple programming exercises. Programming exercise 1's due next Monday, and programming exercise 2 is due the following Monday. And then we do this P3.13.2. That's the third programming exercise where I ask you to write a program in the Racket, but also write a program that does the exact same thing, either in C, C++, MATLAB, Java, whatever you want. We did this I've been doing this for a few years now. And a few years ago, I had everyone, report how long their program was. And the longest program was C. It was about 120 lines of code, I think, executable code. And the average for the imperative group, or the average for the people that chose to use C or C++, my numbers are a little fuzzy. It seems like it was about 60 lines of code. And the average for the people that did MATLAB was like 30 or 40 lines of code because, MATLAB has a lot of prepackaged functions that they were taking advantage of. The Java people were similar, somewhere in between those two. The people who wrote in Racket were way down, and the shortest Racket program was 6 lines of code. But it did the same as the C program that was 120 lines of code. So there can be some advantages there. Now, why do you care? You're never going to program in the functional paradigm. Yeah, you probably will, because as you know, most modern languages are not all one or all the other. They kind of straddle a couple of these lines. So C is specifically an imperative language. However, I have seen large commercial programs that were done in the object-oriented form entirely within C, and they were just done by using human discipline and coding rules. You have also seen C++, a lot of you have. C++ was an outgrowth of C to handle object-oriented paradigm. And so C++ is backwards compatible with C, and therefore it's imperative, but it's also an object-oriented language. Technically, what you have to say is it supports objects. It is not an intrinsically object-oriented language like Java is. It supports objects. Languages like JavaScript, they also support objects. And then, as you know, Python is all over the place, right? Python, you can program in the functional mode, you can program in the object-oriented mode or the imperative mode, or kind of mix it all up. So there are aspects of your programs when you're writing in a commercial space that are probably going to be best done using the functional mode, and you will have programming languages that will likely support that also. So good to be aware of this stuff. So we'll do 2 weeks of the functional programming in Racket. Most of that will be talking about code examples, and then the last module breaks out into just discussing all the language paradigms as kind of a review. We've talked about all kinds of things in this class, and we've identified the imperative, object-oriented, and functional paradigms, but we haven't drilled down to talk about what specifically makes one thing or the other. So this will kind of wrap everything up. By the way, you'll notice the tools that we use, the BNF form of grammar applies to all languages, all paradigms, and that's the standard for how things are defined. When you guys are doing complex data sets, I would recommend that you design them using the Backus-Naur form. Or if you're designing your own language, use the Backus-Naur form. The ideas of computation hold for all of the paradigms. Okay. I believe these are online. They're supposed to be online. Here's the outcomes. And as I've said several times, if you're going to develop a Turing-complete language, or if you're going to claim your language is Turing-complete, then it has to be able to define variables and bind values to those variables, choose which statements execute through if then else, repeat statements, and then produce output. And we've shown that the lambda calculus can do all of those things. By the way, often when I'm talking to particularly like high school students, I'll say, okay, how many of you guys have programmed before? What programming languages do you know? And inevitably people will say HTML. I programmed in HTML and CSS. And I very gently point out to them, yes, that is a good skill, but that is not a fully functional programming language. That is not I can't say Turing computable because they don't know what that means, but it's not a complete programming language, right? HTML is a display language. It literally means HTML, hypertext markup language. It's a markup language for display. It is not a computational language. So, it's nice to know those distinctions sometimes, especially if you're talking to an interview. You don't want to embarrass yourself by saying you know how to program in HTML. Oh, this is from old notes that I didn't go back through. Okay. All right, so we're going to use Racket. And Racket's a functional programming language. Now, again, all modern languages straddle the field. You can do non-functional things in Racket. Technically, you could have done them in Lisp, but it was really frowned upon. In the world of Racket, I'm going to frown upon it because I want you to focus on the functional aspects. But if you were to program in a commercial setting in Racket, there would theoretically be no restrictions on what forms of Racket you're using if you're going to use the things that map more closely to object-oriented or imperative, or if you have to use all of the strictly functional forms. From Lisp, which is the initial language, Lisp begat something called Scheme, and Scheme begat something called Racket. There's a small community of people who are big names in these things. Guy Steele from MIT was a big Lisp guy who was, I believe, instrumental in creating Scheme. And then his students, Matthias Feleisen, and I forget the other guy's name right now, I believe were his students or students at MIT that later transferred, that began teaching at Rice University. They're still there. And they were the beginning of what turned into Racket. There are some books out there. One of the things about Racket, I've shown you the Racket website. I'm not thrilled with their tutorials. I haven't found a great Racket tutorial. However, there was a book by Matthias Feleisen and co-author that I can't remember called The Little Lisper. And when they did Scheme, they rewrote it to The Little Schemer. And I see that they've written follow-ons to that. So I gave you a link to a PDF version of, I think, The Little Schemer, which I believe is a legal copy. It looked like it was not a pirated copy. So I thought it was fair to give you that link. That book is a really good way of learning this material. Probably better than listening to me yap about it. Okay, so Racket, this is the software we're going to use. There's the website. Downloading. You guys are familiar with downloading things by now. They do have the Racket cheat sheet. What I did is I pointed out the stuff that I thought was helpful here, because as I said, I don't see the tutorial. For me, it wasn't the most helpful thing in the world, but the cheat sheet was good. Racket guide and Racket reference, very verbose, but ultimately, when you want to know the definition of a language or how to use a particular term, you have to go to the documentation for the language. And that's what those two things are. And then down off the screen there, down below, is a style guide. I also found that to be helpful. The cheat sheet's nice. It's nice to have the one stop printed out and laminate it kind of thing. That's always nice to have. When you start to run Racket, it looks like this. It's got two windows. Up in the top is the definitions window where you can write programs. Down below is an interactive window that it's called the read eval print loop. And whatever you put into the interactive window will immediately be evaluated, and it will give you an output in that window. So it's like a console input. And I'll be doing a lot of work down there when I'm doing the examples. When you write your programs, you can write them in the definitions window up above. What you do is you write in the definitions window, and then you click that run button, and it will basically, it compiles your program, and it compiles all your definitions. If you actually have actions that are supposed to occur, it will start to occur down in the interactive window below. So that's what we're going to get into as we start to do examples, which I suspect will be on Wednesday. Wednesday, I'll start doing examples, and then on Friday, I'm thinking office hours. However, since you have an assignment due on Monday, we might do an actual lecture with more examples on Friday. We'll see how Wednesday goes, and you guys get to vote. Okay, a couple things that are going to look foreign to you right off the bat, but you get used to in about a day and a half. What you learned in math class was called infix notation. Infix because you put the operators in between the numbers that you're dealing with, or the operands that you're dealing with. In Lisp and other functional programming languages, we tend to use prefix notation. And there's a couple reasons for this. The main reason is, remember, Lisp stands for list processing. And so basically what you do is you have an operator applied to a list. So everything is thought of in terms of lists of entities. And so if I take the prefix notation and I change it, you can see that it's, instead of 7 plus 5 plus 3 plus 2, it's plus 7532. In other words, take the plus operator and apply it to all these numbers, 7532. Hopefully right away you can see the correspondence with lambda calculus. We're taking a function or an operator and applying it to an operand or an argument. So the secondary advantage of that is it's just a lot easier to write, because I can do just one plus sign and then list off, you know, a whole bunch of numbers or entities that I need to be summed, and the operator gets applied to these things magically. Binding values to variables. Now, in the imperative and object-oriented world, you used assignment, the assignment statement. We don't really have an assignment statement in the same way we think about it in the imperative and object-oriented world. When you were said x equals 42, you were taught this means that there is a memory location that we associate with the variable x. And when we say x equals 42, we're storing 42 in that memory location. This is a very machine-oriented description of what's happening. It's absolutely correct. However, the lambda calculus, if you recall, never had an equal sign in there. We never did that. The lambda calculus bound things using the lambda x dot, right? We had free and bound variables. And so we have the binding in terms of, we can say x is equal to 42, say it a little bit differently. We say define x42. Notice there's no mention of memory. There's no real thought about memory. It's more closer to how we thought of the program store when we talked about semantics. Remember, the program store was a set of variable value bindings, and all of the variable value bindings that were in effect at a particular time was the program store at a particular time. So this notion of define x42 maps perfectly to the idea of a program store. You have a set of bindings at any point in time in your program. And being aware of how these bindings were formed will be important, because it turns out that that program store, if you recall how we did the semantics, the program store created an environment in which your expressions were evaluated at a particular point in time. And so the same thing will apply here, and I'll show how that affects the way the programs operate when we get into the program examples. It's a little bit different than how you would do it in the object-oriented world or the imperative world. Bindings, we have the idea of global and local variables. It's just the bindings are global or local, so we can have them local in functions. And remember, what we're going to do is we're going to create functions and build programs using function composition, just like the lambda calculus did. Okay, now list processing. Racket is not too far removed from list. So everything really revolves around lists and handling of lists. One thing that is interesting about these languages, at least Lisp, Scheme, and Racket, there's no type declarations. And so that's great, that's good news. And because if you think of the list as, say, corresponding to an array in the languages that you've learned so far, a lot of languages will restrict the data types of an array. Right, an array has to be filled by the same data type in every location. And here we'll see that lists can be composed of anything. There's no real type declaration. The translator infers the types as you go through. That's good news and bad news. The good news is super flexible. Bad news is you can really hang yourself. You know, you've got enough rope to cause yourself trouble here. Single value is referred to as an atom, and then a list is this just a sequence of atoms enclosed in a parentheses. Note there are no commas in there. You just entity, 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 entity. Always think of lists as having two parts. The first single element, which is an atom, and then the rest of the list, which is a list. The empty list is a list. And as I said, we don't have data restrictions. So we have, numbers, words, numbers and words together. Operators, lists of operators. Remember, the lambda calculus allows you to take functions as input to other functions. So you can have a list of operators or functions in a list. Why would you do that? Maybe you need to do 5 different things to a particular data set. So you call each of those functions one at a time until you do all 5 of them. Lists can be composed of lists. This recurses endlessly. As you noted with the lambda calculus, keeping track of your parentheses was challenging at times. I promise you it will be challenging again. The Racket IDE helps you with that. Also, good coding style helps you with that. Make little functions that do little things rather than embedding all of the details in one large function. So that's what a list is. How do you make them? How do you start to manipulate them? Well, you create them using the list operator. So again, look at the lambda calculus form of that example. List 1391736 means give me a list composed of the numbers 1391736. In other words, what you're saying to the compiler is, don't try to evaluate these things. I'm just making a list right now. But that list, the keyword list, is actually a function or an operator, because what's it saying to do? Make a list out of these things. So again, the lambda calculus paradigm of a function applied to an argument is present there. You can shorthand that with a single quotation mark outside the list. So here I say single quotation mark. It's a similar thing. You're saying, don't try to evaluate this. This is just a bunch of stuff I need to put into a list. So this, as we've seen before, means, hey, add all these numbers together. Apply the plus operator to this list of numbers. But if I write list in the front, it says, make me a list. By the way, the first element in the list is the plus operator. And the rest of it's whatever I put in there, numbers. Creating lists over and over again is a chore, so it's helpful to be able to give them names, and this is where binding comes up. We use the define operator to bind. Define L1 to be that list. Okay, so now every time you say L1, that interactive screen will say, okay, here's L1, and it returns the list back to you. In a function, you can refer to that list as you start to manipulate it. That was my dog, if you heard that. Add elements to the front of the list using the cons operator. Now, when I say an element, I technically should have used the word atom there, right? Whatever you add to the front of the list is treated as an atom. So if I say cons 0 and then I have that list 2, 4, 6, 8, it's just going to add the atom 0 to the remaining list 2, 4, 6, 8. But if I happen to say cons and on my list, the thing that I'm consing is 1, 2, which is a list, to 3, 4, 5, notice that 1, 2 gets added as a single atom, as a single thing, because that's how cons works. It adds one thing to the front of the list. What if you didn't want to add one thing to the front of the list? What if you really wanted to actually take the list 1, 2 and the list 3, 4, 5 and turn it into a single list? You use the append operator. The main things that we're going to worry about, there's really only 3 main tools here. Cons, car, and cooter are the main things you have to remember. cons, car, and cooter. There are many, many other things that you can do with lists, but those are the three basic operations. And if you choose to, you can create your own version of the other operators. Like you could have created append using cons, car, and cooter. All right, what's car? It returns the first element in the list. And what's cooter do? It returns the rest of the list. Now, let's walk through what these are, and then I'll talk about why it's important to have these two things. By the way, why are they named so weird? They're named so weird because in 1958, people were dealing directly with the register addresses. And these are assembly-like mnemonics for register operations that have been lost in the mists of time because we don't tend to worry so much about register operations except you computer engineers out there do. Car returns the first element in the list. So whatever the first element in the list. If you say car and your list is 2, 4, 6, 8, 10, it gets 2 because that's the first element in the list. If you say car and you have a list composed of 2 lists followed by an atom, that first thing in the list is the list 2, 4. How many elements are in this list? Is it 5 or 3? It's 3. Just like with sets, remember sets could contain sets as elements. And if you had a set that contained 2 other sets, how many elements were in that set? 2, the first set and the second set. So since that's the first element in the list, if you car that thing, that's what you get back. And you should literally think of this, the function car literally returns that as a value. Then you're going to do something with that returned value. This will give you an error because the empty list doesn't have a first element. And this will give you an error because 5 is not a list. You can only apply car to a list. Cooter returns the rest of the list, and the thing it returns is always a list. So now I'm going to do cooter to the same 1, 2, 3, 4 things, and I get 2, 4, 6, 8, 10 returns the rest of the list, 4, 6, 8, 10, right? Everything but the car. Cooter of a list followed by a list followed by a 10 gives us the second list followed by a 10 because that first entity was the car of the list, therefore the cooter is the rest of the list. If you union the car and the cooter, or if you cons the car and the cooter, you get the original list back. Cooter on the empty list returns an error. Whoops, says no first element. It has no rest of list. And cooter 5 also returns an error because 5 is an atom, not a list. And what happens if you want to get past the first element? Oh, you can start to do things like that. The cooter of 2, 4, 6, 8, 10 is 4, 6, 8, 10. The car of that is 4. There's actually special terms designed for that, CADR, that kind of thing. But the main thing to think through here is car and cooter. Car gives you the first element in the list. Cooter gives you the remaining part of the list. Cons forms lists by adding 1 element to the front. Append forms lists by taking 2 lists and putting them together. Once you have these ideas of lists down, by the way, we're going to do these examples on, I doubt we'll do any today, we'll do them on Wednesday, and then, you know, the demonstration of these things makes more sense. Additional list operators that are helpful: null, question mark, applied to a list. If the list is empty, then it's true. If it's not empty, it turns false. Length applied to a list gives you the length of the list. The length of the empty list is 0. The length of 2, 4, 6, 8 is 4. The length of 2, 4, 6, 4, 5, 6 is 2 because remember that's made up of 2 lists. It's not 6 elements, there's 2 elements in there. Reverse is helpful because it reverses the order of the list. So sometimes you want to get the last element in the list. It's really easy. You reverse it, car it, and then whatever's left you can reverse back. I'll tell you what, I'm going to stop there and we'll stop when we won't create and compose functions yet. Let me start up Racket and just play with this stuff. And if you haven't installed Racket yet, you really should, because you just want to play with this stuff. All right, so when you start it up, you do want to pick a language, and you want to choose the Racket language. And you can start your code with this. The pound sign is basically a compiler message. Pound lang Racket, which tells the translator compiler that the language you're dealing with is Racket. There's several language packs in here because this is a teaching tool, and I believe they also made it backwards compatible with Scheme, so you could pick Scheme as a language. And then I'm only going to focus on this interactive block. So if I do the interactive block, I say 5, and it says, you told, I evaluated 5, and it's 5. If I put in X, it will say, I don't know what X is. You haven't defined it yet. But if I put in X with quotation marks, oh, that's a string X. So this thing, all it does is read, eval, print, loop. It reads what you put in, evaluates it, and then prints the result back. If I say list 456, it gives me that list back, 456. If I don't want to type out list, I don't have to type out list. If I say list, it says, hey, you still haven't given me X. I don't know what X is. Now it says, oh, okay, I made a list that starts with the string that contains X, 6 and 7. So that's how we can make lists. The plus operator, whoops. It evaluates. So now I said, I didn't say make a list. I said, apply the plus operator to 5798. You always put these things in parentheses. Here's why. If I do this, remember how lambda expressions work? We said an expression could be an expression followed by an expression followed by an expression. So before I hit return, look at that, +3, 4. Now, is that going to be treated by the compiler as, please apply the plus operator to 3 and 4, or is that going to be, here's an expression, the plus operator, here's an expression, 3, here's an expression, 4? And the answer is, it's 3 separate expressions. And it says, I'm evaluating the plus operator, and I've recognized it as a procedure called plus. And I'm evaluating the expression 3, and it has the value of 3. And I'm evaluating the expression for 4, and it has 4. So when you do it, when you do this, what you're doing is you're just giving the machine a bunch of expressions that to evaluate independently. If you want to actually apply the plus operator, the way you do it in these languages is with the parentheses. So if I said list 578, I should get, oh, I've evaluated list, and it's a procedure, and I've evaluated 5 and 7 and 8, and guess what? They are equal to 5 and 7 and 8. I recommend that you play at this childlike simplistic level for a while. Make a list of the plus operator in 3, 5, and 7, and sure enough, it made a list where the first element is the plus operator. I don't know what happens if we do this. I think this should work out the same way. Okay, now making these lists over and over again, like, you know, let's say I did. And now I want to reuse that list. I have to type it all over again. What a pain. So instead, define L1. That's an L. If I use capitals, I'll lose my capitalization. I'll define L1 as that, and notice nothing came back, but when I hit L1 now, it says, oh, that's that list that you defined earlier. So again, this is not quite the same as how memory storage works in the imperative world. It's not quite the same. It's binding. Think of it in terms of the program store. We have bound that list to L1. Now if I do car of L1, I should get 1. It's the first element. And if I do cooter of L1, I get the rest of the list. And if I do cons 0 L1, 0 gets added to the front of the list. If I wanted to do L1 is still that. By the way, notice how the 0 didn't stick, right? Because I haven't changed L1. This is a little bit different from what we're used to. L2, and then I say append L1 and L2. I get that, but notice I don't have a word for that yet, right? Oh, okay, so now I have to say define L3, append L1, L2, and then L3. Now, since I gave it a name, I can hang on to it. By the way, cons L1 and L2, what should it give us? It should give us L1 as a single entity followed by all the other elements of L2. And there it is. There's L1, 1, 2, 3, 4, 5, 6, enclosed in brackets. That's the first element. Define L4 to be cons L1 and L2. Oops, that's no good. And now if I do L4, see, it's that first list, right? Because cons adds one element. So append flattens the lists out at least one level, whereas cons just keeps that thing as a single entity and sticks it in the front. Now if I say car L4, I get the first element, but what's the first element? It's that list, it's L1 back. So again, you can see now, hopefully you're starting to get some glimmers of how, gosh, how does this computation work in the functional world? It's all about traversing these lists and doing things to the data in the lists, or applying the operators that you find in the lists. It's all about that. Okay, I'm going to pause here before we move into function composition. And we'll just do a little bit of functional stuff, and then we'll do a lot more on Wednesday. Hopefully all of you, say I'm an optimist, hopefully all of you have this up and running right now, and you're playing along and trying things out. Again, I cannot recommend enough that you play at this simple level for a while to get comfortable with how you're going to manipulate these things. Any questions?
Professor, I have a quick question.
Sure.
So it was a little ways back, but you did a list using the plus operator as the first atom of it.
Yeah.
And you did the first one, you specified it was list, and then when you hit enter, it came out with the # procedure. And then the next one you did the apostrophe and it just came out with plus. Is there a difference between those two?
There's not a difference between those two. What was happening, and I'm not sure why the system was set up to give you those two separate answers. Ultimately, they're going to be the same thing because the plus sign is a procedure known as the plus sign.
Okay, thank you.
Actually, it might have tried to evaluate that thing even though I told it not to. We'd have to do some experiments to make sure. What if I did? It may have treated the plus. We're going to find out in just a second. That's a good question. Let's do this. Oh, that's no good. L5. And then if I do L5, it gives me that. And if I do car L5, it gives me that. So yeah, it's treating the plus sign as a character in that case. So if I did, I think this will not work. That will not do anything. And here's why. It's treating the plus sign literally as the character plus sign, not as the procedure plus sign. And the way I did it before, it treated it as a procedure. So now if I do define L6, and then I do car L6, I think I'm going to get there. That is a distinction, yep. So that plus sign in the front, I'm sorry, that single quote in the front is not just saying don't evaluate this, it's saying that this is a, treat these things as characters until I tell you otherwise. Notice that didn't work for strings, right? Because if I do X57, I believe, no, it treats everything as just a character. Don't. So that's the distinction. Good question. Okay. I'm going to stop here then and not go into function definition. We'll do that on Wednesday. In the meantime, by all means, play with this stuff. Use the, I think I linked to the little schemer in the Canvas notes. Go through there and look at the stuff they're doing because they ask exactly these kinds of questions and have you actually try them out just like I did here. And usually, as I've said for years to some of you people, you can answer your questions more quickly by writing a simple piece of code and seeing what happens than looking through a bunch of documentation. Okay. Other questions before we go? I don't want to shut you guys off. Okay then. Take care. See you Wednesday.